was talking about the interest in finding the internal loading at various locations, and the reason for that is because we want to find at what point maximum stress happens. We don't know. On this, you actually do some sort of computation at various sections. It's not very, it's not very easy to say at what point your maximum bending moment is. For example, in simple cases like that, you know that if you have a 10K force there, where is the maximum bending moment? At the wall. This very trivial. It's easy to understand. But the case like that, you don't know where the maximum internal loading happens. So you have to somehow do some sort of computation for various cross-section. And then this is a good introduction to the diagrams. We do bending moment, shear force, and no axial load diagram. Diagram means just a simple plot versus various location. So this is just an introduction to that concept. So that's the reason we are interested to do this sort of computation more than one point. Right now we start with just one point, and then we go to another point here, another point here, and then we connect all these dots together to get the final diagram. So at point C, if I want to find internal loading, what should I do first? Somehow you cut it, right? Either take the one on the left or the one on the right. But you immediately realize that whatever I take, I have to compute either this one or this one, the external reaction. So before that, I get the entire thing as a system to find external reactions. And then once I get these two, I either take the one on the left or the one on the right, and then I can find three components right here, right? Then I repeat this example for some other points. So let's first find the internal loading. If I take the entire thing as system, then my FVD would look like something like that, 10K. Then let's say this point is A, this point is B, and this is C. So you have dx, dy, and ay. Why I don't put the ax here? Because it's simply a roller. There is nothing that can hold it up against the x perturbation or axial load. So this is the final thing, the bending moment here, 60K. And that's all you get for that. Should I include CXCY and MX? Why? Because for this big system, it's all internal loading. They cancel out from right and left, right? So now I want to find AY only. Why? Because my plan is I take the one on the left, right? So you can save up your time without going to both BX, BY, because I can just find the reaction at point C with just taking everything on the left. So I just want AY. So in order to get AY, I write one moment equation at what point? B. So continue expanding this equation. So you get 10K times this distance, which is 2, with a negative sign. Both yield 0 at the point B. And then you get negative AY times this distance, which is 2. And then you go to say positive 60K. Should I search for a distance? No, but this is already a couple moment. You don't need to find moment arm. Is equal to 0. Then you solve for AY. AY is equal to, again, as you can easily say, we're still doing 5 steps. System, FVD, equation solve, and verify. So put it in calculator. All right, where is my calculator? Let's put make this mute. So 60 minus 20, 40. Well, this one is 20, 60 minus 20, positive 40, goes to the right, negative 40, divided by negative 2, positive 20, K. And whatever it is, if this is Newton, then it becomes Newton. If this is pound, it becomes pound, right? So that's your AY. So in fact, in the original case, I have an AY this way, 20K. Now imagine if I do the same thing and I get negative 20K. Remember the last step was verification. Is it possible that I get negative 20K with this configuration? Then you say, well, it's either the teacher designed the wrong problem, sometimes it happens. So in that case, you have to do double slider, like that, right? So you can have both positive and negative. Or you did wrong computation, so you have to go back to FTD and see what you have done wrong. Usually the problem either moment computation or FTD is wrong, right? So I have this. Now I have my 20K, so I can get rid of this preliminary calculation. Now I do my main job. My goal was to find the internal loading at point C, which is 3 components at most. Then I take this system right now, and I draw FTD. So if I do that, I get let's call this N, axial load at C, VC, MC. You have 3 components at point C. Then if you walk, you come to this 20K, which I just found it, and 60K. And you come back to the start point. So that's your FTD for the left part of system. So what is the next step? Draw right equation. So if I want to find the axial load, I say, well, for this system, I have 3 equations. Sum of force in x0, that would give me MC, positive or negative? Positive. Nothing comes from VC, nothing from moment. These guys are just in Y, and moment is equal to 0. So the axial load is 0. And that's exactly what we expected. Why? Because I don't have anything that causes the loading in the X. Sometimes you have either an angle force like that, or some sort of other structure hooked up to this structure that cause internal loading, right? Axial loading, sorry, axial loading. Now you go to the next equation, summation of force in Y, 0. So you get negative VC plus 20K is equal to 0. So your shear load, VC, is equal to 20 kilonewton. You remember this load that goes in the Y direction, they call it shear because it causes a shear. It all comes from the familiar word with mechanical engineering word. People who do physics, they don't care if you have shear or axial or bending. They just call it force moment. But we, as mechanical or civil engineer, we call this shear load, right? Now, this guy, they call it moment. We call it bending moment. Why? Because this bending moment can cause this structure to bend, right? So now I write my last equation, summation of moment about any point is equal to 0. If I want to find MC, what would be my best choice? Around point C, because I can eliminate NC and VC simultaneously. You remember, it is another review in vector statics. When we choose the reference point for moment equation, the goal was to choose a point that you can eliminate as many as unknown as possible simultaneously. right, in one shot, right? In this case, C is your desired point, so I put sub C. Then you go and expand it. So you get positive MC, nothing comes from these two, negative 20K times this distance. This distance is 1. And then plus 60K is equal to 0. Solve for MC is equal to, so that's positive 40K, take it to the right, negative 40K. So these are internal loadings. So you have 3 components here. This one is 0. This one is negative 40K. You can either just report like that, or you can say positive 40K and is in the other direction, right? Now, you may say, well, you know what? I took the left system. What about if I take the right system, right? What should you get? Exactly the same thing. And as I said before, it's a good homework. You don't have to turn it in. When you go home, take one on the right, and you must get exactly the same thing. But don't forget, when you take the one on the right, this is always convention that we have here. When you cut a beam like that, right, the one on the right, your bending moment, the positive direction is this way, shear load goes up, axial load is always tension. Now you put the opposite, according to Newton's third law, on the left. So you have this way, and you see the shear load goes down, and the bending moment goes this way. That's the reason that my shear load is down, right? So now I want to do the same thing for some other points. For example, let's say a point here. So A, B, C, let's call this point D, right? So what do I get? Again, let's record this data at C. At C, I have 3 component NC, 0, VC is equal to negative 20K, and MC is equal to negative 40K. Positive, yeah, sorry. Positive, for some reason I saw negative. So now I can safely erase this and go to another point. Again, the motivation to do another point is just to see the trend, and then from the diagram you guess what point is maximum, the critical point, right? So at point D, if I want to find internal loading, I just cut it like that, right? And in this case, I prefer to take the one on the left. Why? Because it's simpler. If you take the one on the right, yes, it's exactly the same, but you have to include all this sort of loading, right? And some of them is unknown, Bx, By. So I just take the one on the left. So that's my Bx, or say Nd, normal force at D, Vd, and Md. And the next thing I have is only a 60K, right? So if I write equations, I get Nd is equal to 0, Vd is equal to 0, and then for moment, you get Md plus 60K is equal to 0. So therefore, at this point, I get Nd 0, Vd 0, and Md negative 60K. Right? Now let's go to another point. And as you can see, this becomes extremely tedious. Every single time you have to pick a point and some sort of starting from scratch, doing everything again. Now that's the reason we will introduce later faster method to find the trend of changing shear and moment diagram, shear and moment forces across the beam. And especially in the next course, structural analysis, we introduce a way called Heaviside function. So instead of doing all these things, you just do everything in just one line. And that one line equation explains the variation of all parameters, shear, moment, and axial load across the beam. That's the fastest method. It's called Heaviside function. But that's what we consider later in this course. Right now, we just do it manually. Now let's go to another point here. A point, let's say a point E, and put it right here. So if I want to find internal loading at E, now this is a good question. I may give a question like this in the midterm or final exam. Just explain if you want to find the internal loading at E. Should I find the reaction at B? Yes or no? No. Why? Yeah, if you cut it here, how many possibilities do I have? Take the one on the right or the one on the left. If you take the one on the left, yes, you need to have BXBY because this is going to be external loading on the system. But what I do here, I take the one on the right. So this is point E, and on my FED, I have a 10K, right? And then I have nothing else except NE, VE, and ME. If I choose the one on the right. So if you choose the part on the right, when you cut it, there is nothing coming from the left. We had a student, even a structural analysis class, even after that, even graduate school, they did not know the way this system, choosing the system works. So every time I say, well, find this, they would incorporate this BXBY. And I say, well, this BXBY is in other systems. You don't need to do anything with that. That's just completely out of your system, right? So here, again, summation of force in X, 0. What do we get? Negative NE, 0. Summation of force Y, 0. And later, when you do more practice, you immediately just don't do a lot of extra work. For example, you can just simply not include this on your FED because you know it's already 0, right? You can save a lot of time later on when you practice. But right now, for the purpose of just showing it education, I just say NE. I'll just bring everything so you can see it's 0. This is going to be negative 10K plus VE, 0. So the shear force is equal to 10K. And finally, moment by point E, 0. Then you get 10K times this distance, which is 1, negative 0, 0 plus ME, 0. So ME becomes positive 10K. So let's write it here. Here at point E. Then you have 3 components. NE, 0, VE, 10K, and ME. I may have done a mistake. Let's check it again. Moment at E, 10K with negative 1, and then ME is negative. Thank you. Who said that? Yeah, email me quiz-mass. You see, the thing is, if you can find mistakes, there are a lot of mistakes. Trust me. If you find mistakes like that, or even go home, watch the video and say, well, in the video, the equation number blah blah is not right. You need a negative sign. Well, you get a quiz mark. Right? You can put a comment in the YouTube. You can put a comment, this is not right, and then I give you quiz mark. So here, I forgot a negative. That means the end result is negative. That means you have to put a negative here, right? So as you can see, this extremely tedious procedure, if we continue, then I can connect these values together to get a diagram, right? It is possible to do that, right? So that's the way we obtain we call it shear diagram, moment diagram, and axial load diagram. So we will talk about it more detail later. I want to just give you a brief explanation, and later when we explain the stress analysis, then we are just ready to do more detailed diagram. Now let's do another example on the actual diagram. So let's say this is a load, this is a beam, and I have a load 2K here. And from here to here is 1 meter, 1 meter, and 2 kilonewton load here, and this beam is fixed to the wall. So in this case, I want to actually draw the diagram. That means I have to do this procedure that I did for several points. I have to choose several points here, and then connect all the points together to get diagram, right? So this question here, find diagrams for V and M and E N, which is normal load at various points across the beam. So first, I do external reaction analysis. If you do the entire thing as system, then you have 2K here, and let's call this point A. So you have AY, AX, and MA. AX, AY, MA, and then 2K. Then you can say AX is equal to 0 summation of force in X0, AY minus 2K, 0, MA. So from here to here is 1 is equal to 2K. Right? So you have that. So let's put it here. At this point, A, I have all my components. Right? Let's record it here. AX, 0, AY. Let's put it this way. Graphically, AY, 2K, and MA is equal to 2K. All right, you don't need this anymore. So now I go ahead and pick my first point. The first point, pick it here, right? Like that. So you get AY, which is 2K, another 2K here, and here you have, and you can call this point, you see from here to here, you can call this point point X, right? We call it point A, B, C, D, E, F, G. Now you reach to a point that you have so many points that you don't have enough alphabet, right? Enough characters. So you just say X, right? And then I can move this X to any point, right? So at point X here, I have X in the normal force in X, the shear load in X, and the bending moment at point X. Right? I have all these three components here. And then I have nothing else because there is no internal loading, gravitational force. The beam is so light. So that's all I get. So again, if you write the equation, you get NX 0, and then you get 2K minus Vx is equal to 0, Vx 2k, and then 2k plus mx. If you write moment about this equation, this point x, you get mx positive plus 2k negative 2k times x is equal to 2k times half is equal to 0. So that's the summation of force in x0, and x is equal to 0, summation of force in y. Then you get 2k with positive, negative v at point x. Then there is nothing else in the y direction, 0, vx is equal to 2k. And then finally, write moment equation about point x. So you already get mx, nothing from these two here. And then you get two contribution. One 2k here, right? Then negative 2k times this distance. This one comes from this shear load here. You see that? And what is this distance? This distance is just half of 1, right? Because I put it at center. So it's negative 2k times 0.5 is equal to 1. So if you solve that, then you get 2k. This is going to be negative 1k. 2 minus 1, 1. Take it to the right, negative 1. mx, negative 1 kilonewton meter. So let's record the data here. At this point, I have n is just simply, I don't write it, Vx is equal to 2k, and mx is equal to negative 1k at this point, right? Now, let's choose another point. Let's choose a point here. If I choose a point here, again, let's say this point still is x, but I just moved it to some other point. Don't choose another character, just point x, right? So if I choose point here, what part of system should I take? Left or right? The one on the right. So you see, you have nx, vx, and mx, right? And you can see that nx is equal to 0, vx is equal to 0, mx is equal to 0, right? Everything is 0. So here, what you actually can say is, well, in my structure, if I connect this dot together, I can draw a diagram. Should I do it right now? So in fact, you can extend these portions, and then you can put x-axis here. That means at various x location. You remember I only did 2x location. One here, one here. When you want to draw something like that, well, you have to at least do 6, 10 different locations, right? 2 locations are not enough. So somehow right now we want to guesstimate it. So x, let's say the y-axis in this diagram is n at point x. Now I have another diagram, x, and the y-axis here is v, shear load at x. And then I have another one at x, and the y-axis is bending moment at x. So normal force diagram, shear, they call it shear diagram, and this one is bending moment diagram, right? So what are the values at this point? At this point, you get, what is my normal force? The normal force is 0. Put a 0 here. You see? There's another color. So if you extend this load, this line, at this point, your shear is, your actual normal force is 0, right? At this point, your shear is what? Positive 2K. So this is 2K. And your bending moment is somewhere here, negative. And this is called negative. You see, this is 0, right? And this is 0 for here, and this is 0 for here. Negative 1K. So I have only, on my diagram, I have 3 points. This is 0 here, then 2K, and negative 1K. Right? So what about this point here? This point, again, yeah, let's use another color. Send it. Then you have 0, 0, and 0. Right? What about this point here? This point A. Well, if you do point A, what is your bending moment? 2K is the one that the external surrounding is applying to a structure. The internal load is going to be negative 2K. What about the normal force? 0. What about the shear load? The shear load is going to be 2K, right? So that means that if you do that, if you draw the shear load, you have a 0 here because the normal force is 0. The shear load is right here, right? And the bending moment is right here, right? And it's equal to negative 2K. Now connect the dot together, you can see that, well, what is the bending moment at this point? Zero, right? Because if you take the system on the right, immediately after that, because this point is singular. You remember in singular point in mathematics that the behavioral function is not defined. You have a discontinuity, right? So, but if you take an infinitesimal from right to the end, then you have 0, no forcing on the system. So the bending moment is 0. So you have another point here. What about the shear? Shear is still positive 2K. And the normal force still 0. So I want to connect all these dots together to get the diagrams, right? So if I do that, then I get, if I connect these dots together, then I get, this is the very last point. At the very last point, of course, again, 0, 0, 0. So connect all this together. There you go. This is the diagram for bending moment. This is the diagram for the shear, and this is the diagram for axial load. You see that? But just manually going to this procedure of manually finding loads at various locations, you can draw diagram. Now, if somebody wants to design this beam and the design parameter is bending moment, just by looking at the diagram, what point are you more concerned in design? Huh? Point A. Why? Because the bending moment is maximum here. Now, if the jump in the shear load is point of design parameter, the jump in shear force, what point you consider? This point, right? Because you see you have a jump. So the diagram, the interesting thing is, I may give you like extra bonus if you go to software and put this in the software, do the loading and say, run it and give me the shear moment diagram. There are software that they can do that. So by just doing this modeling, later on we see the structure become more complicated. This kind of modeling, either manually find the shear moment diagram or use the software to obtain the shear moment diagram. Your job as an engineer is to look at the critical points here. Jump in the shear, maximum bending, And then those are the points that you design for. You consider in your analysis, right? Another example. Maybe we should go back to this example. Yeah, let's go back to this example. I want to draw shear moment diagram for that. So here, what I do, instead of picking points like that, I take the range. Right now I take a range, like x from 0 to 1. Because you see, between 0 and 1, nothing is changing. Then from the 1, you have a vertical load. And then you take it from 1 to 2. So you have to actually repeat this procedure just twice, from 0 to 1 and from 1 to 2, because in this interval everything is same. So that's what I'm going to do right here. This part is a little bit messy. So from how many intervals should I do here for my analysis? We said 3. That's right. Because you see, from here to here, things are pretty much the same. Then it's from here to here, things are the same. Then it's from here to here. Now, if you put another load here at point C, then how many intervals you should consider? 4. We want to minimize the number of intervals. Why? Because for each interval, we are doing exactly the same repeating procedure, right? It's just monotonous. In the next course, structural analysis, we just do 1 for the entire beam. But for that, you need to know more advanced mathematical techniques. So right now, I consider x between 0. Let's put your axis here when you draw, right? This is your x, right? x0 is here. Let's put your 0 here, right? And then you cut it at some point like that, which is located x meter to the left, right? Now I want to draw my FVD. So x between 0 and 2. Don't include the 2, right? So if I do that, I get something like 60 K. Then you get dx, nd, vd, and md. Now, look, this point is at the very center of it, d. But look, my x is some sort of range. It can go from here to here. So I don't write d. I just write x. That's the reason in the previous example, I said let's take that point as an x, because you can move x to any point. Now I can have x from like 1 point, 2 point, or 10 billion point, right? X could be any point, but it should be between 0 and 2. So now if this is my FVD, this 60K, ND, NX, and don't forget again one more time, the x is not exactly at 1. It could be anywhere between this range. MX, NX, and VX, right? Then, what is from here to here? The length of this part of beam. What is this length of part of beam? Just x. Don't forget that. This will count when you do bending moment analysis. You remember we multiplied the shear load here by this distance. Now, this distance was 2, or half of 2, 1, right? Now, if this distance is x, you get some sort of variation. The moment is a function of x2. So let's write the equation. Nx is equal to 0. N at point x is equal to 0. Then negative Vx, nothing here, is equal to 0. And then summation of moment at point x must be 0, which gives you mx plus 60K, 0. So you get a constant thing. When I want to do the diagrams, well, first of all, let's not do n, because n is always 0, right? So I don't occupy extra spacing on a whiteboard for just showing the normal force diagram, because it's identical to 0. So I just consider the first diagram to be the shear, V at X. And I try to make this a straight line. And this is a function of X. So the first station, I have three different intervals, from here to here, from here to here, and from here to the end. So I have 1, 2, 3, right? And I have 1 for bending moment. As bending moment is not mx, is not necessarily 0 like nx. This could be non-zero. So from 0 to 1, from 0 to 2, this is 2, and then this is 4, right? 2 plus 2, 4, and this is 6, right? So from here to here, what do I have? Nx 0, well, I don't care about nx anymore. Vx is 0, so I have a diagram like that. And what is my mx? Negative 60k. So let's say here, negative 60. Okay, this is 0. Negative 60k. And look, unlike the previous example when I only had discrete points, right, 1, 2, now I have the entire range, because this is pretty similar for the entire range. Doesn't matter how many points you pick. When you connect all together, that's the same. It's always negative 60k. So now the next part I caught is from here to here. It's not only at C. It's from here to here. So let's do that again. I have a point there. And this one was 20k, 60, 20k, nothing else. N, I don't care about n anymore because I said n is always 0. V at x, m at x, and what is from here to here? X is the important thing. From here to here is x. Why? Because my reference for drawing the diagram was located at this point. So x starts from here to the point that you cut it. So this entire length is x. X is not from here to here or from here to here. From the beginning to the point that you cut it, right? So again, I write the summation of force in y0. You get Vx negative plus 20k, and this is just simply moment. So negative Vx plus 20k is 0. So Vx, the shear load, is 20k. And now you go to the moment, summation of moment, about point x, which is just this point x, right, is equal to 0. Then you say positive mx, nothing comes from this guy, then plus, I want to compute the moment of this force with respect to point x. What you are right? Force times moment arm. What's the value of moment arm? X1, who said that? Thank you. Who is honest? From here to here, right? If you want to find moment of this force with respect to x, you multiply 20k by this distance. What is this distance? Is x minus from here to here. What is from here to here? 2, right? So from here to here is x minus 2. So you say 20k times x minus 2. Positive or negative? This is positive, right? So this is going to be negative. Thank you. Negative 20k x minus 2. And then I go to the last one. What should I do for that? Simply add it. So it's going to be plus 60. I see, especially in the last quiz or when I was grading, I saw some students multiply the moment with some r. Or when I say just write summation of force in y, you not only write the force, but also you multiply by some sort of r, moment arm. This is just simply force equation. This moment, they are different, right? Is equal to 0. So solve this equation, solve for mx. What do you get? This is just the first time we do that. This is new. So mx, the bending moment at x becomes 20k. X minus 2, take this to the right, right? So you get 20k x minus 2 minus 60k. You can't simplify it more than this. Why? Because x is a range. X is not a number. Now if I put x is equal to 2 plus 1, 3, then you must retrieve the value that we manually compute only at point C. You see that? But this is more general. This is valid for any point, not only C. So that's the advantage of taking X. So let's draw this. Shear force is 20K. So you have a jump. The shear force was 0 previously, and then you have 20K. So you have some sort of jump. So this is 20K from here to here. Right? What about the bending moment? What's the value of bending moment at x is equal to 2 at this point? Put 2 here, negative 60. So you have this one. What's the value of the bending moment at point 3? Negative 40. And somehow you get here. Just put 3. 3 minus 2, 1 times 20, 20 minus 60, negative 40. Now, I'd say at the end of interval, which is 4, right? 2 plus 2, 4. Put x is equal to 4. What do you get? Negative 20. It's still not 0. You see that? So that's going to be your moment diagram. It's a line. And this is negative 20K. It doesn't go to 0. So what about point between point, let's see, this is 2 plus 2, 4. Yeah, negative 20. Then you can do the same thing to draw the continuation of this curve from this point to the end. So when we talk about the shear moment diagram, when we are actually more interested to see the range, not at a particular number. So there is another diagram called a stress. So bending moment, this gives you some sort of a stress that we'll study later. This guy gives you shear stress diagram. So in order to get shear stress diagram, what do you do for average shear stress diagram? It's going to be exactly the same diagram, but it's just scaled. Why? Because you divide this by the cross-sectional area at point X. Right? Because the cross-section area can change too. Right? It's not the same. Example. Let's go back to this, similar like that. And let's say you're the same example here. Let's say you have a variable cross-section area here. You have a cross-section bigger, and then your beam will shrink like that. And I say find the shear stress diagram. So you say, well, here, if the diameter, let's say this is diameter here, D is equal to 5 millimeter, and let's say the diameter here is equal to 2.5. In fact, if you draw it in 3D, that's something like like that. You see? So you can actually, you have a kind of welding here going on. But we ignore that point of cross-section change because that point is so complicated. You cannot analyze that point with the method we study in this course. You have to go to a next level course called finite element method. So here, the area here is equal to pi, the radius. So here the diameter was 5. So the radius is 5.2 times 10 to negative 3 square. And the area here is equal to pi 2.5 divided by 2 square. So put it in calculator. And then also divide this 2K by that. So from here to here, if I want to draw the average shear stress diagram, I get something like, you call it tau, which is equal to V divided by A. Shear force, average shear force, divided by cross-section area. Don't forget, if this is Newton, is meter square. Newton divided by meter square is Pascal. You saw it last class. Right, so it has the same amount of dimension as we have for sigma. Sigma was normal force divided by average cross-section area. Yeah. That's a millimeter. That's a millimeter. If this was, it's always good to pay attention, particular attention to this mm or cm. If this was cm, that would be -2. But this, because it's mm, that means it's millimeter. So you have a -3. So if you want to do that, you divide this 2k, right, from here to here in this section. You see that? You divide this 2k. So you have 2 to 10 to 3 divided by the cross-sectional area there, which is pi 2.5 10 to -3 square. Put it in calculator. Usually it's a huge number. You should expect 10 to 6 or mega. Is 100, almost 100 megapascal. So tau is equal to 101 or 102 megapascal. So if I want to draw it here for average shear force, I have from here to here, I have this value is 102, and you say tau in megapascal. Tau in megapascal, right? MPa. So this is 102, is positive. And then what do we have from here to the end? Just 0, because the shear force is 0. So the conclusion is the hard part is to get the shear, bending, and normal force diagram. Once you get those, the rest is just simply a scale. You just divide it by area, right? So now let's go to one more example. Page, let's start some example from book. Let's go to page Example 7.5. Okay. K, B, C, 4K. Then you have 22K here. So 22, this is B. Let's see, double 4K and 9K, double 9K this way, B, A 12K, and here the cross section area is like, I show it here, a rectangle with the height 35 millimeter and the width 10 mm. 35 and 10 mm. And it says find the axial load diagram, and then you can find the normal stress diagram. Once you get axial load, then you divide at each section by its local area, and then you get axial load. Don't forget, sometimes these two curves are different, the axial load and normal shear diagram. For example, here, if you have just one normal stress here, but you have cross-section change. If you have just one single normal force, the axial load is constant, N is constant. But what about the normal shear in this curve? You're going to have a jump because the area will change, right? So these curves, two curves, are not necessarily just simple scaling. They may have some sort of variation to it. So here, I want to find the normal force here from here to here. So I put my X here. I cut it from the left. This is X0. And this is arbitrary X from here to here, right? Then if I cut it, what part should I take? The one on the right or the one on the left? The one on the left. So you get something like that. This is 12 and N at X. Now in this case, I don't consider the shear force and bending moment. Why? Because I don't have shear or bending. It's only purely normal. So what do I get for NX? NX is positive 12K from here to here. So if I want to draw it, I get, that's your X from here to here is positive 12K, right, from here to here. Now let's go from B to C. So again, you cut it somewhere here, and it's still your X start at the left. Now FVD, I want to draw FVD here. So for FVD, you have 12K and then you have one non-K here, another 9K here, and then you have N at X. And from here to here is what? The length from here to here is X. Always consider that, never forget that. That is enough to destroy your shear diagram. Later we'll see the moment diagram. So if I do that, then I get negative 12K, negative 2 times 9k plus nx is equal to 0, summation of force in x 0. Then you get nx is equal to 30. Yes, 18 plus 12, negative 30, got 30k. So that means you have, from here to here, you have a little bit bigger. If this is 12, let's scale it a little bit. If this is 12, then you have a significant jump. And this value is 30. Plus 30k. Now I want to draw it between here, between C and D. Again, now what part you take? The one on the right. Now when you go home, you just do opposite of what I did. Just for practice, make sure you get the same data. If you don't get the same thing, probably either I have done it wrong or you have done it wrong, then we can figure it out. So from here to here, I cut it from the right, 20. First of all, here I have 12k. Here I have 20k. How come that's possible? When you see this example, you may say, well, something is wrong. If I have 12k on the right, I have to have 12k on the left. But what else do I have there? I have a double 4 this way and double 9 this way. So in fact, if you sum all the external loads, what do you have? You have negative 12, right? Negative 2 times 9k plus 2 times 4k plus 22k. Does it sum to 0? The answer is yes. So that's possible. Always do some sort of investigation before you actually solve the example. So that makes sense. Now, if I draw 20k, I don't consider this 4k because the overall plot is already taken into account. So you don't consider this 4k. You just cut it here and consider this part. So you have 20k here, and then positive n at x. And what is this distance from here to here? Huh? It's not x. From here to here. You say that, see? X minus previous. X is starting from here always. You see, you just scroll it to the left and right, right? So now the question is, what is from here to here? You see, this is the very end. This is the very end right here. And this is the x that is cutting somewhere here. Now the question is, what is from here to here? Length, who is minus? Length minus x. That's right. So the entire thing, right, minus x, because from here to here is x. You see that? The length minus x. What's the length? Length minus x. Why you don't need a length here? Because you're not drawing the moment diagram. If you draw a moment diagram, you multiply this shear by that. In that case, you really need to know the length. But here, the axial load is independent of whatever you have here, right? So n is equal to 22k. Summation of force in x, 0. So here, what do you get? A little bit you go down, but you're not 12. So you're somewhere between. Positive 22k. Now this is for normal force. And at any x. If I want to do a stress, what do? You divide by cross-sectional area, and you notice that the cross-sectional area is the same. in this case. So in this case, your stress, normal stress, which is shown by sigma, I'll talk about it more next class. Shear stress, normal stress. Normal stress, sigma, is equal to N, simply Nx divided by Ax. In this special case, it's going to be the same plot, but just scaled by, divided by cross-section area, because cross-section area is same. But we can have case that is not scaled, simply, if you have variation of cross area across the ring. So next class, we are going to talk more about classification of stress and we will solve more examples.